Today we're going to take a look at section 1.2, which is exploration with patterns. When I was in graduate school, one of the questionnaires that I was using as a part of my research asked the people that I was talking to what their definition of mathematics was. And for a lot of people, their definition of mathematics is a study of patterns. A lot of people also have some definitions about it being problem solving, which is what we did in section 1. So it's kind of interesting that these two sections sort of hit on the two basic themes that people talk about when they talk about what is math. So we're going to talk a little bit about patterns today. A little vocabulary to get us started. A conjecture is simply a statement or conclusion that has not been proven. Another way to say it is that it's an educated guess. It's our best idea of what's going on based on what we've sort of accumulated, the information that we have seen so far. Okay? But it hasn't been proven. A counterexample is something that disproves a conjecture. It shows something else is false. So if I say all dogs have tails and then I meet a dog that doesn't have a tail, that would be a counterexample. Okay? It's just something that proves your statement was false. And then there's two types of reasoning. There's inductive reasoning and there's deductive reasoning. And you've probably heard both of those words before, maybe in this context, maybe not. But they do mean something quite different, in fact, almost opposites of each other. Inductive reasoning is the method of making generalizations based on observations or patterns. For instance, if I saw a list of numbers and I wanted to know what number comes next, that would be inductive reasoning. It's my guess based on the numbers I've seen so far. Okay? It's the speculation. It's my supposition based on sort of concrete, specific examples. If we had people come to class, into our classroom, and they looked at you guys and said, based on the people in this classroom, I believe that every student at OBU is female. You could see, looking in this classroom, why they might say that, right? They would also be wrong, but that's a conjecture based on a specific example or a specific series of examples. Deductive reasoning is the use of mathematical axioms, theorems, definitions, or undefined terms assumed to be true and logic for proof. So typically when we see deductive reasoning, it's something where you've got a set list of sort of concrete examples of something, and then you use those concrete examples to then make a statement based on them. The whole axiomatic system of geometry does this. Like theorems and things that you can prove in geometry are based on a certain series of undefined descriptions of things that you're doing to begin with. It's all based on a certain system of arguments that you're starting with. So the system of geometry is definitely deductive reasoning. All right, a few more. Sequences are simply an ordered arrangement of numbers, figures, or objects. So for those of you who are going to work with the really little kiddos, these might be things that look like shapes, colors, right? You see red triangle, blue square, red triangle, blue square. What comes next? Red triangle, right? So sequence to definitely be shapes and colors. Eventually, as you keep going in mathematics, the sequences start to look more like number series, right? A list of numbers instead. But it's just a different version of the same idea. It's a sequence. It's a pattern of something going on. A recursive formula is a formula based on a pattern established after giving one or more consecutive terms and a rule that shows how to obtain them. For instance, if I give you a couple of terms, I say 5, and then I say 8, and I say, the pattern is we add 3. That's a recursive formula. It's a description of what we do next. So I need somewhere to start, the 5 or the 8, and then you can tell me what would come next based on a recursive description, right? The next term would be patterns add 3. The next term would be 11. Thank you. Yes, it would be 11. So it's just using sort of a description of what the value would be next. And it may look more mathematical in the sense there may be some sort of an equation written down, but there wouldn't have to be. It can just be a description of what happens next. Nth or general term. I will use these interchangeably. Your book uses nth term. Some resources will use general term. This is a formula used to find the certain term in a sequence. This is actually quite helpful. This would be something like saying that I have a sequence and it's based on the equation or the expression 4n plus 3. And I said, find the first term. It would mean you plug in 1 for n. And I say, find the 10th term, and you would plug in 10 for n, right? So like if I gave you the 5, 8, like I did before on the problem, and I said, find the next term, that's fine. You know, the pattern is plus 3 because I told you that. That was the recursive formula. But if I asked you to find the 10th term, you'd have to go through several iterations to get to the 10th term, right? Well, with the general term, you don't have to do that. You just get to plug whatever number it is you need into an already pre-described formula for it, and that's really nice too. So that's a different kind of a pattern description. All right, so we're actually going to talk about two very common types of sequences. We'll actually talk more about that, but the two that we're going to spend the most time on are called arithmetic and geometric. So we're starting with arithmetic. An arithmetic sequence is a sequence in which each successive term is obtained from the previous term by the addition or subtraction of a fixed number. All right, so if I were to write down, let's see what I have on my paper. We'll do an example that's 2, 6, 10, 14. What's the pattern? What's going on in this sequence? You're adding 4 every time. Does everybody agree? Yeah. And we could actually write it in there that way, right? We could say, oh, look, this is plus 4. And this is plus 4. And this is plus 4. And presuming that the pattern continues, which is the dot, 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 then we would say, yes, the pattern is that every time I add 4. This would be called an arithmetic sequence. There's nothing special about adding 4. We could turn this around and we could subtract 4 every time as well. Okay, there's nothing special about it being a positive 4. This sequence has the common difference 4, positive 4. So common difference is simply the fixed number that you're adding or subtracting to the values you already have. Okay, that's called the common difference. All right, so that's what you do when you have an arithmetic sequence. It's all about adding or subtracting a value. The other kind is a geometric sequence. So with a geometric sequence, this is a sequence where each successive term is obtained from the previous term by multiplication of or division by a fixed number. So this is going to be the multiplication version of this instead of the addition and subtraction version of this. All right, so the sequence I'm going to start with is 108, 36, 12, 4. And I want you to see if you can find the pattern. What is it? This one's actually divide by 3, right? Isn't it? Yeah? Okay, good. So this one right here, we divide by 3 to get the next term. Now, since we divide by 3, what we would typically say is that division by 3 is the same as multiplication by 1 over 3. You agree with that? Right? So typically when we're talking about it being the fixed number right here, we're using it in reference to what the multiplication factor would be. So in this particular problem, we would say that this is called a common ratio. That the common ratio is actually 1/3. It's what you would multiply by. But just you have to remember that division really just is the same thing as multiplication in order to sort of construct that in your mind properly. Okay, everybody good with sort of this idea loosely so far? We're good? All right. So what we're going to do next is we're going to take, we have one more sequence, I'm sorry, to talk about. And then one more term, and then we're going to take some sequences. All right, this is another sequence. It's a very fun one. You see this one naturally occurring in nature all the time. It's called the Fibonacci sequence. Fibonacci was a mathematician. This is a non-arithmetic and non-geometric sequence that follows a different pattern, and it's common in nature. So what would that pattern be? Well, let me show you what it is. This pattern is this: 1, 1, 2, 3, 5, 8, 13, 21. And I'll pause right here. Has anyone seen the Fibonacci sequence before? Yeah? I've got a couple people nodding. Okay. It's clearly not arithmetic, right? I can't add from one term to the next. Nor can I multiply, right? Or divide or subtract. None of those work. All right, so any idea what they're doing or what we would have to do to get the next term in this sequence? Add what? Say it again. Just say it louder.
Add 13 and 21.
Okay, so if I want to get the next term, Amanda wants me to add these two numbers together. So let's make sure, looking back at the other numbers, that that process actually worked with the numbers we had from before. So in other words, if I add 3 plus 5, do I get 8? Yes. If I add 5 plus 8, do I get 13? Yes. If I add 8 and 13, do I get 21? Yes. That is the sequence. You're exactly right. Good job, Amanda. So what is 13 plus 21? 34. And then what would be next after that if we wanted to keep going? 55. It's kind of a different one. Is everybody okay with that one? We're not going to use it that much, but be aware that it is a different sequence, and not every sequence has to be this sort of an I added, I subtracted, I multiplied, I divided. It doesn't have to work in an arithmetic or geometric form. All right, we have a definition here. It feels a little bit oddly placed. You'll see why we need it in a little bit, though. The definition is the definition of a raised to the power of n. So it's a definition of exponents, right? If n is a natural number means our counting numbers, 1, 2, 3, 4, and so forth. Then a to the n is a times a times a, and so forth, n times. And if n is equal to 0, which is not a natural number, then we're going to define that a to the n, or in this case this is specifically saying a to the 0, equals 1. So a to the 0 equals 1. I definitely prove that in proportional statistical reasoning, one of the other classes I teach that you will take if you haven't already. But for now, we're going to use it as a definition, okay? So this is a definition description of how it is that we find or talk about exponents. And again, I promise we're about to see why it matters. Example number 1. What we're told to do is 3 things. List the next 3 terms in the sequence. That's thing number 1. Number 2, identify if the sequence is arithmetic, geometric, or neither. And then number 3, find the nth or general term for the sequence. Okay, so we're going to do 3 things. The first sequence, 1, 4, 7, 10. What comes next? 13. And then 16, good. And then 19. Okay, so this was part 1, right? Part 1 is that those are my next 3 pieces, 13, 16, 19. All right, part 2. Part 2 says that we're supposed to find, or to identify if it's arithmetic, geometric, or neither. What is this one? It's arithmetic. Why? Good. It's arithmetic because we're adding 3 each time, so it means 3 is called what? Do you remember? It is the fixed number. It has another name too, beyond fixed number. Fixed number just means it doesn't change. Good. It's the common difference. So this actually has a common difference of 3. All right, so now number 3 here is something that I want to show you how we create it. I will tell you that there is a formula for what I'm about to do. I strongly dislike formulas for formula's sake. If we need a formula for something, that's great. If we can't derive it on our own. But there's really no reason to memorize useless formulas that you're not going to remember 3 days from now. That's my opinion. That is a professional opinion, but it is my opinion. So I want to show you how you can do this without having to memorize something that you're going to forget 3 days from now. Does that sound good? Okay, here's the way it works. If you take a look at each one of these numbers, we already established that the common difference is that we have 3, right? So if I wanted to get, let's just say, for instance, ignore this sequence. If you want to think about something where the common difference of 3 happens, your multiplication table of 3 does that, right? 3, 6, 9, 12, common difference of 3. Agreed? Multiplication of 3's. So what we're going to do is we're going to start this sequence out by saying that we're taking the number 3, our common ratio, times n. If I used this as my general sequence, I would get the sequence 3, 6, 9, 12, and so on. So it's sort of increasing consecutively the way I want it to, but it isn't giving me the numbers I need, right? How much am I off by? Well, if I put in n equal to 1 into 3n, what do I get? I get 3. What do I want to get? I want to get 1. What would I have to do to the number 3 to turn it into the number 1? Subtract 2. You could also divide by 1, but it won't actually end up working for the next term. So I want to subtract 2. All right, so we're going to check to make sure, after we did that, that the second term works. What if I plug in n equal to 2? What is 3 times 2? Minus 2? Is that my second term? Yes, it is. Check it for the third term. If I plug in 3, what do I get? 3 times 3 is 9. Minus 2 is 7. And it works just fine, doesn't it? So, again, where am I getting these numbers? Well, the 3 comes from the fact that it's the common ratio. And it's multiplication by 3 because we've increased it by 3 every time. Okay? And then it's the minus 2 so that it sets it up to have the first term in the right place. It's just whatever I need to add or subtract. Whatever it is, I'm just going to put the plus minus whatever the number is on there, and that resets it to where I want it to be. Okay? So that's how we can do that. All right, we're going to do the same kind of thing on the second one, except for we have a different sequence, of course. Our sequence on the second one is 3, 6, 12, 24. What are my next 3 terms? What's my next term? 48, okay. What's the pattern? What's going on in my pattern here? It's multiplying by 2, yeah, so I need to do multiply by 2 one more time, right? Did you get it? 192 is right, yeah. Okay, very good. So this is part 1. All right, part 2. Is it arithmetic or geometric? It is geometric. Why? Yeah, it's multiplication by the value of 2. So what do we call the number 2? It is a fixed number. It's a common ratio. Good. Common ratio on that one. All right, so again, we were supposed to be finding a general term. How do I find a general term? I mean, it's not going to be the same as I did before, right? Because I don't add 3 every time. I'm multiplying by something every time instead of adding. So what happens? Well, the reason that we had this 3 times n right here and that this worked, because we added multiple times, right? And when you add multiple times, that's called multiplication. And that's what it is. You add something together multiple times, it's multiplication. Well, here I'm multiplying the number 2 multiple times. What happens when you multiply something multiple times? You do get big numbers, that's true. Any ideas? What if you multiplied 3 times 3 times 3 times 3 times 3? Is there another nicer way of writing that? Exponents. Yeah. We're going to see exponents come in on this one because when you multiply something together multiple times, that's exponents. Okay? So our common ratio that we just decided it was, and we decided it was 2, right, is the base of our exponent. Leave yourself a little bit of space. I'm going to move mine over here, actually. So that's the base of my exponent. The exponent is always going to be n minus 1, and I'll explain why in just a second. Okay, but just write the n minus 1 for the moment. Now, in fact, I'll explain it right now, because let's see what happens. What happens if I plug in the number 1 into this? 0 for my exponent. What's 2 to the 0? 1. I get the number 1. Okay? Well, this sequence doesn't start at the number 1. What does it start at? What was it? 3. Well, so this is what I do. I put the number 3 right here. What's 3 times 1? It's 3. Now let's think what happens when I plug in the number 2. Because this is going to be the defining moment of if it works or not. If I plug in the number 2, my exponent becomes a 1, right? And 2 raised to the 1 power is 2. And 2 times my 3 is 6. So the very fact and the reason why I did this n minus 1 at the top is so that I can do that same sort of thing that this minus 2 here did, is it resets it to be the first number. So my first term is the number in front, my common ratio is the number in parentheses, and then my exponent that resets it to the very first value is always going to be n minus 1. It will never be anything different. Both this equation that I just created and this equation 3n minus 2, they can come about by formulas, okay? But the formulas look much more complicated. They're going to have a lot of notation in them, and then it's going to have to be something you have to remember in order to do the problem, okay? So I don't usually show the formulas because I don't find them to be very useful. They aren't necessary. You can do it yourself without any real trouble because they follow a very nice pattern. All right, so now here's your question. What we're doing, is it inductive or deductive reasoning? And I'll wait for you to flip back to decide between the two. In fact, I'll flip back too, so you can see it on my screen if you want to look up here. So inductive reasoning is making a generalization based on observations or patterns. Is that what we're doing? Yeah, it is. You guys just used inductive reasoning. Well done. So this is inductive reasoning. All right. We're going to take a look at one other way to do this. Example number 2. Example number 2 gives us the nth term. All right, look at part A. 5n plus 6. Without doing anything to it, just looking at the expression that is given, can you tell if it's arithmetic or geometric based on the problem we just did before? Which one? Are you sure? It's actually arithmetic. Remember, arithmetic has a number times n, plus or minus something. Geometric's going to be the one that has exponents in it. And this one, 5n plus 6, it doesn't have exponents. This one actually does end up being arithmetic. We'll identify it from another standpoint, too. You don't have to identify it from a formula. I just wondered if you could see the pattern, how it looked like. All right, so if it says, using this nth term, find the first 5 terms of the sequence. So if I have 5n plus 6, and I have the first term of the sequence, what would I do to find that? Yeah, I plug in n equal to 1. So I plug in n equal to 1, what do I get? I get 11. How would I find the second term? N equal to 2, and what would I get? 16. How do I get n equal 3? Plug in 3, right? What do I get? 21. We can plug in n equal to 4, but what else could we do at some point here? Do you recognize a pattern? What's the pattern? It's plus 5, isn't it? And if you don't think of it as being plus 5, you might think of it, as soon as I write the next one down, as, oh, look, the number at the end keeps switching between 1s and 6s. You might also think of it that way. And legitimately it does, because we're adding 5. But it does have that sort of a feel to it. What would the fifth number be? 31. All right, so that was part A. We're supposed to identify the first 5 terms. Part B says that we're supposed to identify, is it arithmetic or geometric? And we've already said, based on the formula, arithmetic. Based on my list of numbers, do we agree? Yeah, it's arithmetic, right? With a common difference of what? 5. The common difference is 5. I add 5 to get each successive term. So this one is arithmetic. All right, let's take a look at the next one. I need to get n equal to 1. So I'm going to get the first term, so let n equal to 1. If I let n equal to 1, what term do I get? 0. All right, let's do n equal to 2. What do I get? 3. N equal to 3? 8, yes. N equal to 4? 15 is right. And n equal to 5? 24. This is part 1 of my example, right, on part B. These are my first 5 terms. Arithmetic, geometric, or neither? Is it geometric? Remember, geometric means I can take a term, I can multiply or divide by something and get the next term. Doesn't work here. There's actually a red flag even before I try. Do you know what the red flag is? 0. I can't take the number 0 and multiply to get the next term. So multiplication's sort of out automatically because of the 0. I could do addition, but it doesn't work, right? 0 to 3 is 3, but 3 to 8 is 5. Now, there is a cool pattern here. I'll show it to you in just a second. Let's actually write down that this is neither. And then let me show you the cool pattern that's going on here that you might not have necessarily recognized at first. So I just told you that a second ago this was plus 3, and this is plus 5. How would I get, if I'm thinking about addition, from 8 to 15? Plus 7. And how about the next one? Plus 9. So that's kind of a cool pattern. Like, you could continue the pattern, right? Not only is it cool that I can look at, say, hey, 3, 5, 7, 9, it's all the odd numbers or something like this, but if I did it again, how do you get from 3 to 5? Plus 2. How do you get from 5 to 7? Plus 2. And how do you get to 7 to 9? Plus 2. It's not arithmetic, but the second time I try to do the plus whatever is going on, it's called the second difference. The second differences are the same, aren't they? They're all plus 2. And that is a pattern we'll discuss more actually next time. One last question before we pause and go back and look at 1.1. Is this inductive or deductive reasoning? Missed my slide. Deductive. Deductive says it's the use of mathematical axioms, theorems, definitions, or undefined terms. This is an equation. That's what it is, right? Or an expression. It's an undefined value, specifically. Assumed to be true. This is it. We're assuming this expression is true, and we use that expression to then make some specific generalization or specific arguments. In this case, what comes next kind of things. So this one is deductive reasoning. Any questions on that? All right.